Hi, my name is Mason Whatley, and I was assigned the topic on glassy carbon. So the article I read was titled Approaching Theoretical Strength in Glassy Carbon Nanolattices, and the study primarily focuses on constructing strong and lightweight mechanical metamaterials through the pyrolysis of polymeric microlattices to help form glassy carbon nanolattices. And the central question behind their research was to determine how can size-dependent strengthening effects and nanoscale architecture be utilized to achieve theoretical strength in glassy carbon. So by leveraging extreme miniaturization, the researchers tried to reduce flaw sizes and enhance the mechanical properties, which ultimately pushed the material's performance closer to its theoretical strength limit. And this study also looked at additional material coatings to further optimize the structural integrity and failure resistance. So the research followed a three-step process and combination of advanced fabrication techniques and material indices to optimize mechanical performance. Miniaturization is the key strategy used here. So by shrinking the structural dimensions to nanoscale, the size of internal flaws is then minimized, which significantly enhances the fracture strength. And the process begins with 3D direct laser writing to create polymeric microlattices, which are then converted into glassy carbon through pyrolysis. And pyrolysis basically involves heating the polymeric structures in a vacuum at 900 degrees Celsius, causing them to shrink isotropically to about 20% of their original size to then form dense glassy carbon with improved mechanical properties. And some structures were coated with a 10 nanometer thin layer of alumina coating, which was used to enhance buckling resistance. But the material indices used include M1, M2, and M3, where sigma is the compressive strength and rho is density, to identify the materials with optimal strength to density ratios. So M1 is the basic strength to density or strength to weight ratio, which maximizes specific strength, and M2 accounts for failure modes, so it maximizes the stiffness to weight ratio, and M3 is the measure of material strength relative to the mass, and this one basically maximizes the strength to density ratio. So the design focuses on developing lightweight structural supports with high compressive strength and low density. And the materials examined include glassy carbon, alumina-coated glassy carbon lattices, and carbon honeycombs, chosen for their unique mechanical properties and potential for extreme miniaturization. So the first part of the study looked at how does lattice size affect the compressive strength and stiffness of glassy carbon nanolattices. So this was explored by looking at the effects of miniaturization on compressive strength and stiffness. So the figures show stress-strain curves for different lattice sizes. The left graph reveals that smaller lattice structures have significantly higher compressive strengths due to the minimized flaw sizes. More specifically, the smallest lattices achieved compressive strengths up to 310 megapascals at a density of 0.35 grams per cubic centimeter, which demonstrated a high strength to density ratio. And this enhancement was due to the miniaturization, reducing the critical flaw size below 30 to 70 nanometers, which helped approach the theoretical strength of bulk glass carbon. Additionally, the graph on the right shows stress-strain curves for alumina-coated nanolattices, which demonstrate the further increase in strength and stiffness. The alumina coatings provide the additional buckling resistance due to its high Young's modulus. And the smallest lattice size resulted in stresses in a Young's modulus of up to 450 megapascals and 5 gigapascals. However, it was found that the relative gain in strength diminished as lattice size decreases, showing that miniaturization is the dominant factor influencing strength at nanoscale dimensions, where material failure rather than buckling becomes the limiting factor. The second part of the study looked at how does nano honeycombs topology influence mechanical performance. In this part of the study examined the impact of honeycomb structures on compressive strength and stiffness. The figure on the left presents the stress strain curves for honeycomb structure nanolattices, showing that this topology achieves high compressive strengths of 1.2 gigapascals at a density of 0.6 grams per cubic centimeter. So with the Young's modulus, it also reached at 10 gigapascal. So this performance is attributed to the honeycomb's stretching dominant deformation mode, which efficiently distributes the load and it minimizes buckling. So the SEM images illustrated on the right show the honeycomb architecture, revealing the thin walls and a uniform triangular pattern that optimizes load distribution while maintaining minimal weight. So this topology enhances the strength to density ratios, which outperforms traditional bending dominant lattices. The study also showed that alumina-coated honeycombs also showed enhanced buckling resistance, so it further improves the compressive strength. So the Ashby diagram plots the compressive strength versus density for various carbon-based materials, including bulky glass carbon, glassy carbon lattices, alumina-coated carbon lattices, and carbon honeycombs. Overall, bulky glassy carbon showed lower strength due to larger internal flaws, while glassy carbon lattices showed lower density but competitive strength to density ratios due to its nanoscale architecture, while the alumina-coated carbon lattices showed higher compressive strengths due to alumina stiffening effect, and then honeycomb structures achieved the highest performance due to its topology. But the diagram also shows the extreme nature of miniaturization and the structural optimization that shifts glassy carbon towards its theoretical strength limit by reducing the flaw sizes and enhancing the load distribution. The final material selection of glassy carbon nanolattices was made due to their unmatched strength to density ratios achieved through extreme miniaturization and optimized architecture. So by minimizing the flaw size below 30 to 70 nanometers, these nanolattices approach the theoretical strength limit of bulk glassy carbon. And by considering honeycomb topology that further maximizes load distribution and alumina coatings that provide enhanced buckling resistance, these combinations of lightweight design, high specific strength, and flaw insensitivity makes glassy carbon nanolattices the optimal choice for applications that require maximum strength at minimum weight. But some of the future work that I found that should be explored more from this article is maybe long-term durability, scalable manufacturing, and possibly an alternative coatings to potentially enhance ductility.